Hi, everyone. My name is Wes Michaels. I'm in the Chin Lab in Stanford University in the Department of Chemical Engineering. Today, I'm going to be talking about my work towards building an atomistic model for PEDOT oligomers. I'm going to share my screen real quick. All right, here we go. So, again, this is going to be the focus of my talk today. As a very brief introduction to PEDOT PSS. I see that the title's a bit cut off here. So I have PEDOT PSS devices can achieve excellent transport and material properties. And PEDOT PSS is a conductive polymer complex formed by two different polymers shown here at the top. One on the left is PEDOT, it's the conductive agent, and it's composed of relatively short oligomeric repeat units. It's positively charged during synthesis and maintains that during solution and processing into the final film. It's terribly insoluble in water, unfortunately, and as a result is synthesized and solubilized in the presence of the highly anionic PSS, which is composed of much longer repeat units and is much more flexible. PEDOT PSS has applications in a variety of different modern devices, including transistors, biocompatible materials, as well as for energy generation and storage. Well, in this case, energy generation, we have thermoelectrics and solar cells. And to keep the introduction brief, I'll fast forward to sort of one of the problems that the engineers face when working with this material, and that is optimizing its electrical, for example, transport properties. And here I have one example of that, where in a 2017 study, researchers were interested in maximizing both the stretchability and the conductivity of PEDOT PSS films. In order to do so, they looked at 12 different additives in a informed and educated, but nonetheless trial and error approach, and ended up ranking them on the x-axis in order of decreasing conductivity here. And I'm going to show you two different additives to emphasize the point that the molecular details in these sorts of systems are quite important. So for example, if we look at additive number 6, is the EM-IM TFSI ionic liquid. It's very commonly used as a component of the processing of PEDOT PSS films. You can see that we achieve a conductivity of 720 Siemens per centimeter, which is on the same order of magnitude of the most highly conductive PEDOT PSS films. However, if we make a small change just to the nature of the cation here, we can see a dramatic decrease in the conductivity, and this actually has implications for the morphology as well. So again, this hand-picked example demonstrates that atomistic details in the system are quite important. And as a computational person, in order to build a reliable model, or in order to have a reliable model that can help inform these experimental design questions about maximizing, for example, the electrical conductivity, we want to have an accurate atomistic model that captures these details. So in order to do so, there are kind of two main steps. I'll be only talking about one today. So the first is finding a density functional theory method to bridge the gap in length scales between really, really trustworthy ab initio data and the classical length scales, the order nanometer and I guess nanosecond time scales that we want to be able to study. I won't be talking about that work today. In short, we were able to find that the omega B97XD long range corrected density functional does the job quite well. Today, I'm going to be talking about how we fit an atomistic model to the density functional theory representation of PEDOT. And what that amounts to is generating a variety of different DFT data and fit some sort of classical equation to it. And what we're fitting is a relatively common, actually almost ubiquitous equation that is used in molecular dynamics or MD simulations. And I've displayed the Hamiltonian of the system here. So I guess this is the internal energy of the system. Has kind of three classes of components. The first are these non-bonded components, which essentially all atoms are going to be interacting with. They come from relatively common forces that we'd expect atoms to be interacting each other with. So we have the van der Waals force that represents these sort of dispersion interactions, as well as the Coulombic force that represents charge-charge interactions. And overall, these help maintain the overall spatial extent and density of the material. Next, we have these bond and angle parameters, both of which are fit to harmonic spring type equations. These help maintain the overall shape and structure of the molecule. And finally, we have another set of bonded parameters called dihedral parameters that represent twists about any given bond, a set of bonds that connect 4 atoms. And those end up maintaining the overall conformational shape, or spatial extent of the molecule. So we're fitting all of these parameters, essentially, and the ones highlighted in green are the ones that we're actually going to be fitting in this model. We leave the Leonard-Jones parameters untouched in order to mean compatibility with the generalized amber force field, or GAF. And the Coulomb parameters are fit with a relatively standard procedure that we did not endeavor to change in this work. So we underwent this procedure for 2 different types of PEDOT. One is the highly doped bipolaron state, and the other is the neutral state. We did both for 6 monomer repeat units, or hexamers. The reason we did that is that the experimentally observed charge density in PEDOT films for highly doped PEDOT is 0.33 charges per monomer, about 1/3. So what that means is that our bipolaron here is the lowest, the smallest viable repeat unit that we can use to understand or to represent the +2 charge spinless charge carrier that is observed quite commonly experimentally in PEDOT. So that's kind of the smallest we can go, but it's still a relatively large molecule as far as density functional theory calculations go. And we do the neutral polymer as well, both to establish some contrast, as well as give some understanding, for example, in cases where it's electrochemically dedoped. And we're fitting a variety of training data, or rather we have a variety of training data that we're fitting to, displayed here at the bottom of the slide. We have the ground state geometry, vibrational energies, and torsional profiles of molecules, as well as some energy matching data, which I will explain later, and this regularization parameter that penalizes any deviation away from GAF parameters so that we can maintain a bit more interpretability in our final result. And for the remainder of the presentation, I'm going to walk through some of the learnings that we have from these middle 3 data fitting procedures, as well as showing some high-level impacts on the overall conformational flexibility of the molecule. So first, just want to show that the optimization does materially improve the force field's ability to fit the training data. So what I have here are 2 different plots, one for the bipolaron and neutral case. On the y-axis, we have the objective function, which is just a linear the overall objective function is a linear combination of the individual loss functions for each type of training data. And we can see that both for the bipolaron and the neutral case, starting from the 0th step, which represents that of the GAF parameters, we can see that there's a relatively quick convergence to some much lower minimum, meaning that we're doing a better job fitting the training data. And that if we turn our attention to the right panel here, looking at the neutral optimization, we can see that this optimization is quite stable, meaning that if not finding a global minimum, which would be difficult to do in such a large, or difficult to prove in such a large parameter space, we're at least finding a stable local minimum that we can achieve. So I'm going to talk about, again, as I said, the vibrational, the torsional, and the energy matching kind of takeaways from this fitting procedure. So for the vibrational data, I have here a computationally convenient representation of a vibrational spectrum. On the x-axis, we have the vibrational mode index, which is essentially that if we take the 80 atom PEDOT hexamer and we were to calculate every single possible vibrational mode from that, we would end up with 234 of them. And that's what we have here. We sorted them in order of increasing vibrational energy. And that's exactly the plot that you see here. So in the black dashed line is our training data, the omega B97XD calculation for this molecule. This is for the bipolaron. In red, we have the initial fit, or the initial guess of the GAF parameters. And in the blue, we have our optimized MM parameters. We can see that looking at the overall root mean square error of each trace relative to DFT, that optimization yields significant improvement in the overall error in the force field. This is showing that holistically overall, we're achieving a much better fit. And it's instructive to look at 2 different types, or 2 different subsets of this graph, just to learn a bit more. And one is these low energy modes, kind of in the bottom left corner here and shown in the inset that just popped up. These are vibrational modes that extend over the entire molecule and involve low energy perturbations. GAF actually does a relatively good job fitting these. And by tweaking the optimization procedure a bit, we were able to maintain that fit. A more significant improvement in the fit is seen in these this range here that I'm circling with my mouse and is shown in the inset. And these modes are largely characterized by carbon-carbon bond deformations, like the one shown here, that really highlight changes in bond length along the conjugated backbone. And we're able to see that this work, or our optimization, yields significant improvement in the relative error compared to GAF. So again, this is reassuring since we know that just from our sort of the conventional aromatic to quinoid transition when a polymer is doped, this is showing that we're able to capture the charge geometry interaction a bit better, at least insofar as we can represent that in the vibrational spectrum. Next, we're going to talk about the torsional profiles, specifically along the backbone, because those are expected to grant the highest degree of intramolecular flexibility. What that means is I'm going to show a brief video here where we have our PEDOT hexamer and we're twisting about the bond in between the two middle red circular spherical atoms. So it looks like this. So we're doing this sort of twist, and we imagine that we can plot the energy of that twist, as a function of how far it's being twisted, the backbone angle phi. And that plot looks like what we have here, where I have the GAF initial guess in gray, as well as the training data in the colored traces. These come from density functional theory. What we see is that off the bat, GAF does not do a very good job fitting these peaks. If we look at first the bipolar on case where I have the M2, M3, M3, M4, and M1, M2 traces, what those mean is that so the M1, M2 is in between the first two monomers. M2, M3 is in between the second and third monomers. M3, M4, I'm sorry, I think my screen's cutting it off here, but that's the one I have torsion about monomers, M3, M4. So that's this middle rotation here. So you can see that as we twist different bonds along the backbone, we're actually seeing a different peak or a different height of the torsional profile. We believe that comes from the length of the carbon-carbon bond, and it's like a relative balance between the sigma and pi-like character of the bond. So we can see right off the bat, again, we'd hope that our model is able to capture these differences. And especially, we'd hope that a model is able to capture the neutral case as well, where we can see that GAF does it pretty severely overestimates the height of this torsional barrier. And just for brevity, I'll only show one case here. This is for the middle M3, M4 dihedral. But we can see that our optimization definitely does a better job fitting the relative values, both of the local maximum here at around phi equals 90 or negative 90 degrees. Also the local minimum that is close to 180 degrees, we're able to capture better. And we maintain relatively the curvature of the fit about the potential energy surface minimum, which means that we're sort of at a high level, we're capturing the overall shape and relative energies of the spectrum a lot better, which we expect to grant additional accuracy in modeling the conformational flexibility of the molecule. The last set of data I want to talk about are the energy matching data, which in brief are looking at, for a given snapshot, the energy density functional theory relative to the energy of that same configuration predicted by molecular mechanics. If we were to take all these individual EDFT and EMMs and plot those as XY pairs, like this one little cross that I've hovering my mouse over here, and do that for a whole bunch of points within a simulation, we'd be able to get a plot that looks like this, where a perfect model would fall along this, exactly along this XY parity line. We can see right off the bat, GAF doesn't do a very good job. Partially because it's not representing the same potential energy surface minimum as the DFT data are. But if we do this, sort of follow this iterative procedure where we train our force field with the data that I've shown previously, we sample with MD, we run molecular dynamics simulations to obtain new conformations, we calculate the DFT energies of those conformations, and then we add those as new training data for the next round of iteration. We see that as we go through different multiple rounds of the cycle, we're able to both get closer to this parity line, as well as decrease the overall, this is the standard deviation of the distribution. We're able to narrow that as optimization rounds continue, which is good news. Also, if we look at the, for the final set of training data generated by the last force field, but that training data hasn't seen before, So these are essentially like true tested data. We're able to see that the optimized force field does a great job predicting that, both in terms of the error and the closest to fit to this parity line, meaning where the fitting procedure is a successful one. So some of the upshots on the conformational flexibility of the molecule, we have looking at 2 different backbone dihedral distribution profiles sampled from MD simulations of the finalized force fields. For the bipolar on, we can see that because of the strong rigidity of these double bonds along the backbone, that perhaps fortuitously GAF does a relatively good job predicting them, as we can see in the red curve here. However, there's a qualitative difference in that the GAF curve does not have any sort of extra local minimum around here. It actually stays at 0 probability throughout the entire microsecond long simulation. Whereas here, for all the different bonds along the backbone, we see that the optimized force field shows that some of these states are being accessed, which has implications for the morphology of the film. As you might expect, looking at the dihedral profiles, the neutral hexamer compared to GAF has a drastically different fit. And that is, those data are reflected in sort of this overall picture of the simulation. So what I've shown here is that as we go from looking at, it's perhaps easiest to look at the undoped case first. As we progress from red to green to blue, these are different conformations of the polymer as we evolve the simulation. So you can think about, they're just all superimposed at once and visualized just with points, just for clarity. So we can see that GAF has a very little conformational flexibility. So this is a 120 mer, which is much longer than normal PEDOT chains, but we did the simulation just to kind of emphasize the conformational flexibility of the different molecules. We see that GAF is relatively rigid, almost completely rigid actually. It just stays in its initial configuration and fluctuates, almost flutters back and forth. The optimized doped force field predicts a little bit more fluttering, to be imprecise about it. We see greater twists and turns in the back along the backbone, and this optimized force field for the highly doped case. And as we decrease the doping to a completely undoped state, we see that we get qualitatively different behavior for the flexibility of the molecule. So this is an interesting result in that it shows that the doping state is going to have a really, really important effect on the conformational flexibility of the molecule. So this is an opportunity to investigate more for future work. So with that, in summary, we were able to use a reliable density functional theory method to generate force field training data. We then optimized the classical force field that fits those data well, and we found the largest improvements in the energy matching potential energy surface data, as well as the torsional profiles. And with that, I would like to thank my awesome peers and mentors in the Chin Lab and otherwise at Stanford, as well as my funding sources. My email is wpm216@stanford.edu. It'll be at my poster as well. If you have any questions, insights, comments, or just want to use the force field, let me know and I'd be happy to talk.